Welcome to lecture 23. In this lecture, I want to continue to discuss Schwarzschild solutions to general relativity. Einstein field equations, the equations of motion for general relativity, are generally hard to solve. The last lecture, we discussed an analytic solution to the Einstein field equations, which was found by Carl Schwarzschild. The solutions is written in spherical coordinates, and it's given by the metric tensor being a diagonal matrix that involves a part that looks like the Minkowski space metric tensor and a part that involves a function a of r, where a of r is given by 1 plus a constant divided by r. In this lecture, I want to discuss the physical meaning of the Schwarzschild solution. First, I want to talk about the constant that appears in the function a. I will write the constant as minus another constant, which I call rs, the minus just being at the moment just convention, but it will turn out that rs is positive. So if I do this, then the function a becomes 1 minus rs over r. So rs is an unknown constant that has to have the dimension length in order for this to be a dimensionless ratio. We call rs the Schwarzschild radius. And in the following, I want to relate rs to things that we know about. To do this, note that the Schwarzschild solution for the function a is a solution for the 0, 0 component of the metric tensor. So the 0, 0 component of the metric tensor for the Schwarzschild solution is minus 1 plus rs over r. If we are at large distances from the center, so if r is very, very large, then this combination is very small, and g naught becomes very close to the metric of Minkowski. So the r to infinity limit, the limit where we go far away from the center, is the same as the weak field limit of the Einstein field equations that we talked about in earlier lectures. In particular, if we look at the metric tensor g naught, which I write as minus 1 plus rs over r, we know that in the weak field limit, this is equal to minus 1 plus twice the Newton gravitational potential, which itself fulfills the equation of Laplace phi is 4 pi g times the energy density epsilon. Since energy is the same as mass, we can integrate this equation here and find that the gravitational potential is given as minus g times m over r, where m is the volume integral of the energy density in a ball of radius r. So that's the complete mass that's encapsulated in this volume. So then we have the gravitational potential that takes the form of a constant divided by r that goes into the metric component g0, g00. And on the other hand, we also have this exact solution to the Einstein field equations that have the same property that we have a constant over r. So we can relate rs to this constant that appears in the solution of the Newtonian gravitational potential. And this is not an approximation because we do this identification in the limit where r is very, very large. So these two sides are actually the same in this limit. So we find that if we do this identification, we get a value for rs. The value for rs is 2 times g times n. And that means we get a result that links this constant that appears in the Schwarzschild solution to the total mass that is inside a volume of radius r. So if we take this radius and plug it back into the form of the metric component g00, that's the exact form of the metric 00 component. And since this is an exact solution, we can look at what this metric component does, not only for large values of r, but for all values of the radius r. So we already know that for large values of r, the metric component G00 just goes to -1. That's the same as in Minkowski space. So the metric is nicely behaved for large radius, and we just get flat spacetime for large distances away from the center. However, as we decrease r from infinity, the metric component G00 is growing. And in particular, for the critical value of the radius equal to the Schwarzschild radius, we have that this term here just cancels the 1, and we get that at the Schwarzschild radius, the metric component G0 is just equal to 0. Remember also that we have other metric components, such as the GRR metric component, and this one involves the inverse function a. This is the function a. So that means that if G00 is 0, then GRR at the same point is just infinity. And these are just statements that say that the metric tensor is singular at this point Rs because it doesn't have an inverse and it contains infinities. We call this point Rs equal Rs the horizon, and that term will only make sense when we talk about physical objects that actually sort of have no matter outside their Schwarzschild radius. So if you look once more at the metric component G00, then another thing that we should notice that besides the singularity that G00 vanishes exactly at the Schwarzschild radius, there's a second singularity present, namely the one where r here goes to 0, because in this case, the metric component G00 just blows up. So there are actually two singularities of the metric tensor in the Schwarzschild solution. So we find that the Schwarzschild solution, while nicely behaved and regular for large distance from the center, has singularities at two radial positions. There's one at radius 0, and there's one at a radius r, which corresponds to a sphere in space. So it is singular at all points on this sphere. In the rest of the lecture, I want to talk about what these singularities mean physically. In particular, I want to address the questions of whether these are real singularities in the sense that something bad is happening when you fall and pass one of these singularities, or whether they are just harmless and just something that we don't need to worry about. In order to have a case where there are harmless singularities, let's take a look at so-called coordinate singularities. And for those, we want to get some insight from familiar polar coordinates. So what I have in mind is you take a two-dimensional space, R2, and instead of using Euclidean or coordinates x and y, you use polar coordinates r and phi, so that x and y are given as r cosine phi and r sine phi. And in terms of these coordinates r and phi, the metric tensor is just giving us a diagonal matrix 1 and r squared. Of course, we want to invert the metric tensor for instance, having a metric tensor with upstairs components. In this case, we just have to take the inverse of this diagonal matrix, which is again a diagonal matrix, which now has the entries 1 and 1 over r squared. Clearly, this metric here is singular at r0 because it has an infinity in the lower right-hand corner. Also clearly, this singularity is completely harmless. It's not a problem of the manifold because two-dimensional Euclidean space R2 is perfectly fine. It's just a question that we have chosen coordinates that seem to have a problem at this point. So R0 in polar coordinates is not a real singularity. It is an example of the coordinates we employed. And basically the idea is that once you have a singularity like this and it's not a real singularity, you just employed bad coordinates for this one point of your manifold. We call these types of singularities that are not real coordinate singularities because they can be taken away and made regular just by using different coordinates. And in our case, it's obvious how to do this. Instead of employing polar coordinates, you go back to Euclidean coordinates, and the point R0, which is just the center, is perfectly fine in Euclidean coordinates. So it is just a coordinate singularity. Okay, so now that we know that there are harmless singularities, how do we actually decide whether the singularities that we found for the Schwarzschild solutions, those at r is 0 and r is equal to rs, are real singularities or just coordinate singularities? In order to do this, we need to have some sort of test or observable that is coordinate invariant, meaning it is the same no matter which coordinates we choose, because otherwise we won't get away figuring out which part is coordinate dependent, which one isn't. Fortunately, we do have coordinate invariant quantities. An example of this would, for instance, be the Ricci scalar R, which, as we know, is diffeomorphism invariant because it's a scalar. And that means that it takes the same value no matter which coordinates we employ. Another potential coordinate invariant quantity is other scalars that we can build, such as armu, which again, because all the indices are contracted, constitutes a coordinate invariant observable, and as such will basically tell us about any problems that we have in our spacetime, no matter what coordinates we use. There are a large number of other possibilities we can do. For instance, we can look at R alpha beta gamma delta, R alpha beta gamma delta, where R alpha beta gamma delta is the Riemann tensor, and we can sort of build another coordinate invariant scalar from just contracting the Riemann tensor, for instance. So the point is that having these observables at our disposal, we can calculate them for any examples where we have a metric tensor. And if for the location of our coordinate singular, or for the location of our singularities that we found, we can see what the values of these are. And if they are singular at these particular points, then indeed it's a real singularity. It cannot be sort of removed by using other coordinates. But if, on the other hand, they are perfectly fine, meaning regular at these singular points, then what we have is just an example of a coordinate singularity. Okay, let's do this now for Schwarzschild. We have the explicit metric for Schwarzschild. We can use our computer program to calculate the Ricci scalar, and we find that for the Schwarzschild solution, the Ricci scalar is just identically 0. This doesn't really tell us very much because R0 is just a requirement for the solution to be a solution of Einstein field equations in empty space and vanishing cosmological constant. So this statement that it's 0 everywhere actually doesn't tell us anything. Similarly, we have the case of R mu. R mu is 0, and that is also 0 for all R, because again, if we have an Einstein field equation, a solution to the Einstein field equations, it must fulfill R mu is equal to 0. So then R mu squared must be 0 for all R, simply because we have a solution to Einstein field equations. So neither one of these examples really is a good test of whether we have any singular behavior. So let's look at the third option that I listed in the previous slide, which is Riemann tensor squared. Again, we can calculate this for the Schwarzschild solution, and we find this is equal to 6rs squared over r squared. So now we have something that is not trivially vanishing, and it gives us a result that depends on the radius r, and we can evaluate it at the 2 points that we found to be singular points of the metric tensor in the polar coordinates that we used for the Schwarzschild solution. In particular, we can investigate the point r is equal to rs. If we plug it into Riemann squared, we find that Riemann squared at the point r is equal to rs is just 6. 6 is not divergent, so that means that the point r is equal to rs, the Schwarzschild horizon, is just a coordinate singularity. It can be removed by just choosing more clever coordinates. And in fact, we'll find examples of these more clever coordinates as we go on. By contrast, if we look at the other singular point that we identified, the point r is 0, the Riemann squared tensor here diverges. So we find that r is 0 is actually a real singularity. This is unlike the case of the polar coordinates we discussed a few slides back, where r0 was just a coordinate singularity. Here, for the Schwarzschild solution, the real singularity is at the center, and r is rs, the Schwarzschild horizon, is a perfectly regular point that is just a coordinate singularity in the spherical coordinates that we chose to express our solutions. And this concludes the present lecture.